Discover science with us. Fun, wonder, and stories.
Lily and the bee, come learn and see. Science is fun for you and me. Lily and the bee, come learn and see. Science is fun for you and me. Hi, this is Princess Jenna Ross, your host for the day. Welcome to the incredible world of physics, where we unlock the secrets of the universe one mind-blowing concept at a time. And today we're diving into a phenomenon that makes the world go round: kinetic energy. Get ready to explore the energy of motion. Why do bikes accelerate faster than scooters? How much energy does a speeding bullet possess? And how do wind turbines harness the power of wind? These questions and more will be answered as we unravel the mysteries of kinetic energy. So buckle up and let's embark on this thrilling journey of discovery together. Unleash the power within you. Ever wonder what makes things move? At its core, kinetic energy is the energy possessed by any object in motion. Whether it's a tiny atom or a roaring lion, anything that moves has kinetic energy. This energy is responsible for all the motion we observe in our daily lives, from the graceful flight of a bird to the rolling movement of a bowling ball. Imagine a cyclist gliding down a hill, feeling the wind in their hair as they pick up speed. As their velocity increases, so does their kinetic energy. It's this very energy that propels them forward, allowing them to conquer new heights and distances. But wait, there's more. Kinetic energy doesn't just depend on velocity. It's also influenced by another critical factor: mass. The more massive an object is, the more kinetic energy it possesses for a given velocity. Consider a pair of skaters, one novice and the other a seasoned professional. Both glide across the ice at the same speed. However, the experienced skater's body mass is greater due to muscle and bone density, giving them more kinetic energy to maintain their balance and execute intricate maneuvers. Now, how do these factors, mass and velocity, come together to determine the amount of kinetic energy an object possesses? Let's dive into the fascinating formula that defines kinetic energy. In the world of physics, kinetic energy key is calculated using the following formula: E equals a half mv. In this equation, m represents the mass of the object and v stands for its velocity. This simple yet powerful formula reveals the relationship between these variables and provides a quantitative measure of the kinetic energy of an object. When an object's mass increases, its kinetic energy also rises proportionally. For instance, if you double the mass of a moving object while keeping its velocity constant, its kinetic energy will also double. Similarly, when an object's velocity increases, its kinetic energy changes proportionally to the square of the velocity. If you double the object's speed, its kinetic energy will quadruple. Let's take a closer look at how this formula applies to real-life scenarios. Consider a car traveling down a highway. The car has a mass of 1,500 kilograms and is moving at a speed of 20 meters per second. Using the kinetic energy formula, we can calculate the car's kinetic energy as follows: K equals a half 1,500. Gg 20 meters per second equals 300,000 joules. This means that the car possesses 300,000 joules of kinetic energy due to its motion. Another example is a bike with a mass of 10 kilograms moving at a speed of 5 meters per second. But wait, there's more to kinetic energy than meets the eye. Objects can also rotate about an axis, such as a spinning wheel or a planet orbiting the sun. In these cases, kinetic energy can be expressed in two ways: translational kinetic energy, which depends on the object's mass and velocity, and rotational kinetic energy, which considers the object's moment of inertia and angular velocity. For example, a figure skater spinning on the ice possesses both translational and rotational kinetic energy. Their translational kinetic energy results from their movement across the ice, while their rotational kinetic energy comes from their spinning motion. By understanding both types of kinetic energy, we gain a deeper appreciation for the complexity and wonder of the physical world around us. Ready to test your knowledge? Pause the video here if you want to test your understanding of the key points covered so far. Remember, the faster an object moves or the more massive it is, the more kinetic energy it has. Now let's continue our exploration of kinetic energy. Applications of kinetic energy, from engineering marvels to sports triumphs. Kinetic energy has countless applications that shape our world. In engineering, it's harnessed to generate electricity, power transportation systems, and drive industrial processes. Wind turbines, for instance, rely on the kinetic energy of wind to produce clean, renewable energy. By capturing the kinetic energy of flowing water, hydroelectric dams generate electricity on a massive scale. Sports enthusiasts understand the importance of kinetic energy as well. A baseball player swings a bat, converting potential energy into kinetic energy to send the ball soaring through the air. A tennis player serves an ace, utilizing the kinetic energy of their body and the racket to propel the ball towards their opponent. Even the graceful movements of a dancer involve kinetic energy, transforming potential energy stored in their muscles into kinetic energy that expresses itself through motion. These are just a few examples of the many ways kinetic energy is applied in our world, whether it's generating power, propelling vehicles, or enhancing athletic performance. Kinetic energy plays a crucial role in shaping our daily experiences. Work, energy, and kinetic energy. Now let's explore the intriguing relationship between work and kinetic energy. The work-energy theorem states that the work done on an object is equal to the change in its kinetic energy. Imagine pushing a shopping cart across the floor. The force you apply to the cart is said to do work on it. As a result, the cart gains kinetic energy and starts moving. Mathematically, this can be expressed as the work done on an object. W is equal to the final kinetic energy Kef minus the initial kinetic energy K. W equals Kef K. This theorem highlights the connection between work and kinetic energy, emphasizing that work is measured in the same units as kinetic energy, the joule. The work-energy theorem has numerous applications in physics and engineering. It allows us to analyze the motion of objects under the influence of various forces and helps in solving complex mechanical problems. One practical application is in the design of machines and structures. By understanding the relationship between work and kinetic energy, engineers can optimize the efficiency of systems such as conveyor belts, gears, and bearings, ensuring smooth and efficient movement. Grasping this concept opens doors to understanding other crucial topics in physics like power, energy conservation, and momentum. What can kinetic energy do? Kinetic energy has the power to shape our world in countless ways. In the realm of transportation, kinetic energy is harnessed to propel vehicles forward, whether it's a speeding car or a soaring airplane. The kinetic energy stored in their motion enables them to traverse vast distances with ease. But that's not all. Kinetic energy also drives the wheels of industry. Manufacturing processes rely on the controlled release of kinetic energy to form intricate components and products that enhance our daily lives. The rhythmic hum of machinery is a testament to the transformative power of kinetic energy in shaping our world. Moreover, kinetic energy plays a pivotal role in electricity generation. Wind turbines and hydroelectric dams capture the kinetic energy of wind and water respectively, converting it into electrical energy that powers our homes and sustains our modern society. But the applications of kinetic energy don't end there. It finds use in various fields such as sports, entertainment, and scientific research. In sports, athletes harness their kinetic energy to excel in their chosen disciplines, from the graceful movements of a ballet dancer to the powerful swing of a baseball bat. Entertainment industries utilize kinetic energy to create thrilling experiences for audiences, whether it's roller coasters at amusement parks or the captivating motion of a kinetic sculpture. Scientific research also benefits from our understanding of kinetic energy, enabling scientists to explore the fundamental laws of motion and conduct experiments that advance our knowledge of the physical world. Understanding kinetic energy empowers us to appreciate the dynamic forces that shape our world, drive technological advancements, and enable inspiring feats of human endeavor. Conclusion: as we wrap up our journey into the fascinating world of kinetic energy, we hope you've gained a deeper understanding of this fundamental concept. Remember, kinetic energy is all about the energy of motion. It's what makes things move and interact with each other in our everyday lives. From the simplest of objects to the most complex of machines, everything that moves possesses kinetic energy. We've explored how kinetic energy depends on an object's mass and velocity as well as its applications in various aspects of our lives. So the next time you see a cyclist speeding down a hill, a car zooming past you, or even a leaf falling from a tree, remember that kinetic energy is at play. Keep asking questions, stay curious, and never stop exploring the wonders of science. Who knows? You might just uncover the next big breakthrough in physics. Once again, this your host, Princess Generos, as well as Lily in the story. Thank you for watching. See you on our next fun science and stories.